little bit.
Okay, great. So I don't plan to talk much about like very like recent results or anything like that. I'll only be talking about things which have been known since, I don't know, like maybe 2008 or so. Just like basics on the theory of optimal transport and gradient flows over this space. But this problem is motivated by sampling, and in particular, like this these connections between the fields of optimization and sampling. So I drew this little analogy up there where in optimization we want to minimize a function f. In sampling, the corresponding problem is to sample from a known density pi, which is of the functional form x squared minus v. So thermodynamics v is like their potential function. And like the reason why you would want to sample from this distribution, for instance, like a major motivation is just Bayesian statistics. Like you write down some posterior distribution, and then you want to sample from it in order to actually do inference. But besides that, this is like a pretty basic algorithmic problem. So I want to understand how we can design algorithms for this. One thing is like, although like sampling from convex bodies has been studied a lot within TCS, this is a little bit of a different flavor. In particular, like the emphasis here is like what ideas from convex optimization can we bring over to sampling? And like when you sample from convex bodies, in my opinion, the enemy is just that you don't really know what the shape of the convex body is, so you don't know like how to explore well. But in this setting, I'm going to consider potential function v, which is both like strongly convex and smooth. And then because of this, we can actually like use gradient information about v to guide where the sampler is going. And so the focus here is more just like how do we kind of bring over like all the tools from optimization, continuous optimization to sampling. And the starting point is like the most basic algorithm for optimization is this gradient flow. You just solve this ODE where your direction of movement is the minus gradient of your function, the direction of steepest descent. And what I want to talk about today is how the Langevin diffusion can be viewed as the sampling analog of this. In particular, it's going to be a gradient flow over the space of measures with the geometry of optimal transport that I'll define. So that's the main thing I want to convey.
So what are you trying to sample from?
The density pi.
Which is what? What's v?
V is just a function that I'm allowed to query.
Function from where to where?
RD to R.
V is a function from RD to R.
Yeah, just a real valued function over Euclidean space.
So a good example is v is x squared over 2 or minus x squared over 2, I guess. It's a Gaussian distribution over, x can be a vector with the norm of x squared. And then it would be something from the Gaussian distribution. That's an example of, because x squared over 2 is convex, this is what they call log-concave. So you can think of v as a quadratic, I think, no, if you want it to.
Yeah, these assumptions on v mean that in some sense it's like close to quadratic.
Can you expand those conditions maybe a little bit? But what's the second
condition?
What's the first condition?
The first one is that it's strongly convex. The Hessian is lower bounded by some constant alpha. And then the upper bound on the Hessian is needed for discretization, but actually not needed for the continuous standard depth.
This is the Hessian is a matrix, so what norm is this?
I mean, like all the eigenvalues are uniformly between alpha and beta.
Okay, and then the second one. So you're saying this condition in itself says it's close to quadratic?
That's the definition of strongly convex.
Okay, but so
think of a univariate case. When you have a convexity, if the second derivative is positive, here you want it to be strictly positive, strictly above 0. Okay, that's strong convexity. Just you see that, like in a quadratic function. If the function was x squared, the second derivative is 1. It's way above 0. So that's what the strong convex function be. And then if you take exponential to this negative power, this type of distribution that is called log-concave. So one example of, I guess, Sinho mentioned, one example of a log-concave distribution is the uniform distribution over a convex set in any dimension. This turns out to be log-concave. And some algorithms for sampling convex from convex point of view. I guess we'll see other algorithms.
Yeah, so this setting is chosen because it's sort of the cleanest, like mathematically, but to like draw the analogy with convex optimization, I guess it was realized in machine learning that a lot of problems can be like formulated as convex optimization, like logistic regression and SVMs and SDPs and all that. So here, like I'm looking at strongly convex functions, but this kind of captures like the just like regular convex functions because you can just add a regularization term and you can trade that off. So I won't really discuss that, but yeah, you can think this is maybe the most basic setting to try to understand how fast we can sample. And of course, like these assumptions are going to make the sampling problem actually tractable. Like we know that if you want to sample from some crazy multimodal distribution, then that's going to be like impossible in general or intractable. But this is going to be an easy problem, but the question is like, how do we like refine our analysis, develop algorithms inspired by optimization and so on. So like before I talk about the actual like Langevin diffusion, I'll just like briefly mention some work that's going on in this area, and I'll like compare with the model result from optimization that we want. So here's the corresponding theorem for optimization. So under these settings, the minimum number of queries to F and its gradient to output X. And so this is the query complexity of strongly convex and smooth minimization. It scales as square root of the condition number times like log of 1 over the desired accuracy.
Condition number is the lower bound on the alpha.
Condition number is the ratio between beta and alpha.
Yeah, the largest and smallest eigenvalues of the hash. Yeah.
What does it say there with fx what?
F of x minus the minimum of f. Like your epsilon suboptimality.
So this is simple vanilla gradient descent.
No. This is Nesterov's accelerated gradient descent.
It's well, yeah. So a normal gradient descent will give alpha.
We just give kappa without the square.
Without the square. Kappa. Okay.
So this is the presence of acceleration. Right, this was the breakthrough in optimization that gradient descent is not optimal. You can accelerate and you can put this square root factor here. Also, there's this is a theta, so there's a matching lower bound, which says that no query algorithm can do better than this, at least in high dimensions.
The x is a real number, or isn't it?
Yeah.
So what is the number of queries would be?
Like how many times? This is like in an oracle model. So at any point x, I'm allowed to ask for the value of f of x or the gradient of f of x.
The x in this bound should be the optimal is
Kappa.
Oh,
That's condition number.
Oh, sorry. Yeah.
What is this number?
This is
Oh, okay. So that's a parameter of the function.
yeah. This defines the function class. Like beta over alpha is the ratio.
I see it in with that.
Yeah.
So, like, is the matching lower bound for any function or like?
No, this is a worst case lower bound.
Okay.
Like for any query algorithm, there exists a function for which that algorithm will perform this badly. So this gives us like a very complete understanding of the difficulty of this problem, because we've identified like what is an optimal algorithm for this, and we know the intrinsic difficulty of this. So you could ask the same question for sampling. So here we make queries to V and the gradient of V, and then you want to get epsilon close to the distribution pi in some metric like total variation or whatnot. And so this question is like the query complexity of sampling. So what's kind of the state of the art here? So for sampling,
So for sampling, you have access to V, I guess, not to pi.
yeah,
Yeah, so you have the potential is there.
yeah, but only up to the normalization constant. Okay, so for sampling, it's like much less understood, but the best upper bounds that we know so far are the complexity is scales as kappa times d to the 1/3 over epsilon to the 2/3 to get Wasserstein distance less than epsilon.
What is D?
D is the dimension.
So we are out to the D.
Yeah. And this was work by Rochi Shen at UW and Yintat Li.
Again, before what will, yeah, so this is a clever algorithm. What could the simple algorithm give? Just D instead of D to the third?
Yeah, and then also epsilon squared instead of epsilon to the 2/3. Yeah, but you can see like this also scales like polynomially in 1 over epsilon, so it's hard to get very precise solutions. There's other results if you want more precise solutions. Yeah, rates like this. And this is to get a variety of metrics, like you could consider W2, GB, square root of the KL, etc. So this is also like recent this year. Also by 2 concurrent groups. One was myself with Jason Otto at UPenn. And another was a group led by Yongshin Chen at Georgia Tech. Okay, but
Good question. W2 is what is, or is some, it's not the Wasserstein distance.
yeah, it's the
So
Wasserstein
which
distance.
you will define, but also in total variation distance, the normal. And these are some random walk algorithms, continuous time, random walk.
Yeah, they're kind of like fancier versions of discretizations of Langevin, but you have to also replace the process Langevin with something else, and then
How does the W2 relate to the total variation?
in general, they're not comparable, but under our assumptions of like strong Log-concavity, if you get a KL bound, it will imply both W2 and TV because of transport inequalities and conspiracy inequality. Yeah, I mean, like the choice of metric, like you do care, but like for us, let's not worry about the metric too carefully right now.
Yeah, so what would be the trivial algorithm that's obviously with D? Is that something very easy or?
So if you discretize Langevin and you analyze it in a very naive way.
Yeah, so Langevin, I guess people don't know, you wrote it down, but you can say what is that.
So this is like the complexity that Langevin achieves, at least if you do a naive analysis. And then if you do some like averaging and some more refined analysis, you can achieve this.
What is the algorithm?
You discretize the Langevin diffusion.
What does that mean?
I'll like get to it, but really like this talk, I'm not going to talk much about algorithms. I'm really going to talk about the continuous time picture. This is just to give you a sense of like where the field is at currently. So, I mean, the point is there's just like a lot of open questions. One is like, you can see that there's these 2 different complexities. The dimension dependence is worse if you want better dependence on epsilon. It's like not clear whether that's like really necessary or not. Another question is like, in optimization, we know that this acceleration phenomenon is possible, like getting square root dependence on the condition number, and this is like completely open in sampling. Also like lower bounds. There's a couple for sampling, but very, very far from the upper bounds. You can see like compared to optimization, the rates for sampling are dimension dependent. And this like, to me, seems intrinsic. It seems like sampling is just harder because you have to explore the space some more. But we don't have any lower bounds that would tell you that polynomial dependence on the dimension is necessary. So there's like open questions, but also been a lot of progress recently.
Can I finish the answer to that? The discretization there is, if you look at the Langevin law and you look on the other side gradient, but you add some noise. The random walk is add some noise. In this case, it's Brownian mode.
Go where the function is larger,
Yeah,
but not
but not directly. Yeah, you want to explore the space, so you add a random noise that's independent, which is going in all directions.
and that would converge to the.
This converges to the, yeah, I guess it's not obvious. And it depends on the constants you use, right?
Like the fact that the Langevin diffusion converges to the distribution pi will also be a consequence of what I talked about today.
Of what?
It'll be a consequence of what I talked about today, that the Langevin diffusion converges to pi. Oh, yeah.
But I guess it's some continuous version of why the global dynamics converges in the discrete application.
I mean, because it has the right stationary distribution?
Yeah, because that's the right stationary. That's what you have to prove in any algorithm for sampling. The first, before convergence result, speed of convergence, you want to show which converges to the right thing. And often it is easy to set up a process whose stationary distribution is the desired one. So this happens to be a good one for this kind of Log-concave distribution.
Yeah, but of course, like if you can prove convergence rates, then that will imply in particular that you have the right stationary distribution. Okay, so what is the idea I want to explain today is this simple model, which is if I look at I'm now going to look at the law of the Langevin diffusion. Let's denote by mu t is going to be the law of xt. Instead of looking at the process xt itself, which is a stochastic process, I'm going to look at what's going on at the level of its law. And then we're going to see that if you look at the evolution of its law, it's going to be a gradient flow in the space of probability measures. So I'm going to write P2 of RD. So this is the space of distributions over RD, but with finite second moment, with respect to a certain geometry on the space, and that's going to be the Wasserstein distance from optimal transport. And to specify a gradient flow, I also need the objective function, which is going to be the KL divergence with respect to the stationary distribution.
So does it matter what the starting position is? Do you care?
I mean, the gradient flow is just saying like wherever you start, I'm always going to travel in the direction of steepest descent of this function.
I understand, but the question is that the bounds are for any starting point, I guess.
You mean like those bounds?
Yeah.
No, those are like specific.
Starting point, but you didn't specify the starting point of the. But when you start this process.
You're asking like where is the dependence on the initialization?
Yeah, if there is one. Yeah.
I guess like I'm usually a simple way to do this is just to say that V is minimized at 0. This means like basically you know roughly where the distribution is. You can find the minimizer V just via convex application as well.
So, and then you start at the minimum.
Well, you start at certain distributions, like depending on the algorithm. But like as long as you know roughly where the mass of V is, you can design what is a good initialization.
So what's the second part of the law, the square root 2 BT?
So this is a Brownian motion.
Oh.
Yeah, this is a stochastic differential equation driven by Brownian motion. At the discrete time level, it just looks like, well, we'll see that you're kind of just taking steps in this gradient direction, but adding some Gaussian random variables at each iteration.
So how does that noise come in there? Can you explain a little bit, well, what does it mean that that's gradient descent if it has noise in it?
Because I'm looking at the law, and the evolution of the law is deterministic,
What do you mean by law?
like the probability distribution of xt. So if I consider the curve mu t as a function of time, this is deterministic evolution. And I'm going to write down like what is the evolution of mu t. It's going to be a PD.
Oh, that's why I've never seen that before. So what do you mean if it's randomized? How can it be deterministic?
Oh, but this is the law at time t, right? So when you look at the probability distribution at time t,
Probability distribution over all possible.
I mean, this is a distribution over RD.
It evolves, right? The distribution evolves. You
Yeah.
start from a distribution concentrated in a
So
point.
you add the noise to the.
And then you add the noise, just like in the market.
You have an evolution of the distribution.
Yeah,
This is the same thing you would get if you did this gradient descent on this other space.
Yes. All right, so the starting point is like we need to find a formula for how this mu t evolves. So this is basically like stochastic calculus. I'll just like derive it though. This is what's usually called the Fokker-Planck equation. It also goes by other names like Kolmogor's equation, but basically like for STs, we know how to write down how the law evolves. The way we do that is we track how the expectations of test functions evolve along these processes. And then by duality, if you know how the expectation of every test function evolves, then you know how the law itself evolves. So to do that, I'm just going to consider like a discrete approximation to the Langevin diffusion, which will become accurate as you take the step size to 0, but okay, so this is for small h, this is what the Langevin diffusion looks like. I start at xt, I go take a step in the direction of negative gradient of v with step size equal to little h. And then this is the Brownian motion. So just from the distribution of the Brownian increments, then the amount of Gaussian noise I'm adding at this iteration is just has covariance 2h times I day. Okay, and then I want to understand, like, let's say that I have a test function.
you move a little h in the gradient direction, and then you sample from a ball of radius 2h around it.
Not a ball, a Gaussian.
I got that. Okay, but it's almost. Yeah.
Almost, yeah.
Or maybe it is. Yeah.
Okay, so what I want to know is like, can I understand like how the expectation of this test function looks like at a short time h later? If I can understand this for all test functions phi, then I've understood, I'll show you how this leads to the equation for the evolution of the law. So this we just do by Taylor expansion. Well, I guess yeah. let's call this guy square root 2h times xi, where xi is a standard Gaussian. And then we want to expand this guy with respect to h. Okay, so we have xt, and then we'll have the first order Taylor expansion.
So you think of phi z now.
No, phi is not.
Phi is arbitrary, okay, you expand the xt.
Yeah, I'm going to Taylor expand phi. Okay, so I get this for the first order expansion. And then the whole like point of stochastic calculus is that in stochastic calculus, it's not enough to expand to first order, you actually need to expand to second order. And the reason why is if you think about the sizes of the things that we're adding here, this one has size h, and we're only going to look at things up to first order in h. So up to second order, like this term doesn't matter anymore. This one you only need first order. That's like usual calculus. But this Gaussian random variable actually has size square root of h, because h is a variance. So because this has size square root h, even if you go to second order, you will pick up terms of order h, which are still meaningful. In fact, like the second order term, the only term that's still meaningful is when you look at square root 2h times xi, this quadratic form against the Hessian. All the other terms we don't have to worry about because they're little o h. Okay, and then when you look at this expression, so xi is this Gaussian random variable that's going to be independent of the xt that we started with. So this has a 0 expectation. So far we have phi of xt minus h times this inner product between the gradient of phi and the gradient of v. And then we have this term. So you'll pick up, okay, the square root 2h, square root 2h plus 1/2 will give you plus h. And now, so when you take the inner product of xi's with some matrix, then you'll get the trace of this matrix. And the trace of the Hessian is also called the Laplacian. So we'll call this the Laplacian. Oops, the expectation of the Laplacian. Okay, and then plus like little h terms. So this is the extra term that's contributed by Brownian motion. So now like I've identified the change up to first order in h. So this gives me an equation for the time derivative. It tells me that the time derivative is just equal to what I've identified here.
It's just something else with this.
Yes. Okay, so now I know exactly how every single test function phi is going to evolve along this continuous time process.
But can we get some information about these terms, the two terms in the derivative? So the first is the expectation of the gradients of the function of xt with the.
Yeah, this is just coming from the drift of the Langevin diffusion. We know it has a drift in the direction of minus grad v, so you get this term. This is the new term that comes from stochastic calculus, and this is just the effect of the Brownian motion. And we'll like interpret these terms later. Yeah, but to see why this gives the equation for the law, let's rewrite the left-hand side as when I take the expectation of phi of xt, it's the same thing as the integral of phi with respect to the law of xt. And in turn, if this thing has a nice density, then this is the same thing as the integral of phi against the time derivative of the density. And then this right-hand side, we can also write as an integral against Vt because these expectations are all involving xt. I'll write it as Laplacian of phi minus this inner product times Vt. So this quantity is usually called the generator of the process. It's a differential operator that characterizes the dynamics of your process. But if I want to compare the left-hand side and the right-hand side, what I want to do is rewrite this left-hand side. So it's just the integral of phi times a bunch of stuff. So I could compare with the left-hand side and identify what the time derivative of Vt is. So the way that you rewrite the right-hand side to only include phi is you do integration by parts. Okay, so what happens when you integrate by parts? First of all, the Laplacian, you can just move over to the Vt. Like, don't worry about all the details of integration by parts if you haven't done these calculations in a while. You can just trust me. So here, like the Laplacian, you can move over to mu t. And then here I need to integrate by parts to take the gradient off of this phi. And the way that this goes is this minus becomes a plus, and then you get the divergence of the rest of this stuff, which is mu t times greater than phi.
Can you write the definition of a Laplacian of phi?
So the Laplacian is a trace definition, which is the sum over all the coordinates of the second derivatives in those directions. Okay, so if you compare this expression with this expression, this tells you what the time derivative of the density is. So that equation is called the Fokker-Planck equation, which I'll record here. And you have two terms, like one, this Laplacian of mu t is really the encoding the Brownian motion, and then you have this extra term coming from the drift. If I didn't have this extra term coming from the drift, this would be the heat equation, which is how the density evolves under Brownian motion, just by itself is the heat equation.
The definition of divergence.
So the divergence of a vector field V, so V is like it assigns to every point to Rd another vector. That's the vector field. So the divergence of V is just the sum. You can also write it as like the dot product of the gradient operator with V. And this is going to be the sum in all the directions of the derivative in the ith direction of the ith component of the vector field.
It's a vector. It's a scalar, so.
Yeah, it's a scalar.
It's a scalar, okay, like again.
Okay. Right, so we'll come back to this equation for the lunch one. Like the reason why I derive it here is to like later identify it with what the gradient flow of the KL will be. But like now I need to like actually give some background on optimal transport and then actually define these gradient flows.
So just 1 second before you go there. In the case that V is strongly convex, does it say anything about the divergence directly? The fact that V is strongly convex?
Not really. It's also like mixed in with the mu t here.
We don't know anything special at this point. What mu t you want to figure out for this one?
Yeah, so far as hasn't come in, like you can use the strong convexity of V to do coupling arguments at the level of the SD. But the strong convexity will only come in at the very end. Okay, so let's Let's now discuss optimal transport, which will provide us our geometric understanding of these dynamics.
So at this point, you just derived the formula for the evolution of the mu t, of the measure of the law.
Okay, so optimal transport has also been pretty popular in recent years. It started with this question by Monge, which is just if I have like a pile of dirt and I need to send it to some ditch, what is the cheapest way of conducting this movement? And the way that we formulate it is we think of this, okay, we think of a mapping T. This is going to be what's called our transport map. So T of X tells you like for every position X in the dirt, like where in the ditch should I send it to? And there's like two extra things that we need. One is like the constraint of actually transporting. We want to make sure that this dirt actually goes to the ditch. And the second is like, what is the optimal way to do this? So the constraint, the way that we phrase it nowadays is that we actually think of the source and the target as two probability measures. These like probability measures will capture like where the dirt is and where the ditch is, and also like the density at each point. And then the constraint that we should transport from mu to nu is written by saying that T pushes forward the distribution mu onto nu. And in probabilistic terms, what this means is that if X is a random variable drawn from mu, then I want, after I apply the mapping T, I want this random variable to be drawn as nu. Okay, so this will map one distribution to the other at the level of particles. So this is a transport constraint. And then what is optimality?
For optimality, you need the cost.
Yeah, so okay, so you specify some cost function, and this cost function is the cost of transporting X to T of X. And then we find the transport plan T, which minimizes the average cost of transport.
It's like a continuous weighted matching problem.
Yes, yeah.
Like a perfect matching problem you want to.
Yeah, like for discrete distributions, this is like exactly matching in some sense. Okay, so this is optimal transport, but Monge formulated this, I guess, like in the 18th century or something like that. But there is like not much mathematical progress on this for a long, long time until Kantorovich in the 20th century. And Kantorovich made a big breakthrough on this problem. And actually, like the story of this is really like the birth of linear programming. So he was like, of course, like this problem is kind of motivated by economics, like how do we route like products to warehouses, stuff like this. And Kantorovich was interested in these things, and like his work on finding a relaxation of this problem is really like the birth of linear programming, and that eventually led to the Nobel Prize in economics. So his idea was simple, like this transport, it's really like hiding one extra constraint, which is that for every point X in the dirt, there's a unique place that we're going to send it to in the ditch. So we're not allowed to like split up some part of the dirt here into multiple locations here. He just said like, let's allow for this mass splitting. And then we'll actually have a tractable problem. Like note that this constraint is pretty nasty, so it's hard to optimize this thing. So what he suggested was that I'm going to instead minimize overall couplings of my two measures. And then I just find the average cost under this coupling. So coupling means that the gamma is a distribution on the product space over where these distributions are defined. So if these are both distributions over RD, then this is a distribution over RD cross RD. And then I want the marginal distributions to be mu and nu respectively. Okay, so equivalently, I want to find a joint distribution xy such that the individual random variables are drawn with the distributions mu and nu respectively. So this is a coupling, also well known in probability. So now
They can be correlated in any way as long as the margin are not of.
Yes.
You are looking for the optimal.
yes, and now this is really like a convex problem because this constraint of having the right marginals, this turns out to be like a convex constraint on gamma, and this is a linear functional of gamma. And when you really have mu and nu being discrete measures, then this is truly a linear program. So of course, like this means like we can compute this and so on, but also like we can use this to do some theory. So because this problem is much more tractable theoretically, it actually led to insights about the original Monge problem, where you really restrict gamma to be induced by transport. Okay, so
this is really a relaxation of the, right?
yes, it's a relaxation.
It's a linear programming relaxation of the, it allows you to split parts.
Sorry, why aren't the values the same?
So like in the first place, like a transport map might not even exist. Like let's say that I transport from just a distribution over 1 point to a distribution which places mass 1/2 on 2 points. There's like not even a single transport map that can move from here to here. But yeah, in general, like the value of this will be smaller because I'm optimizing over more possible ways to transport the mass. But we'll see, like actually in certain circumstances, the Kantorovich problem will give us a solution to the original Monge problem, which is pretty interesting.
Like replacing the permutation matrices with doubly stochastic matrices with
Yes.
discrete distributions.
Yes. So if mu and nu are uniform distributions over like n points each, then yeah, this the set of couplings becomes a set of doubly stochastic matrices. We know that the extreme points of that matrix are the permutation matrices, because we're like minimizing a linear functional over a polytope. There has to be a minimizer at a vertex, and then so that in particular implies that there is a permutation matrix that will accomplish this. But we'll see like a manifestation of this in like a different set, which is like continuous distributions. Okay, so I want to sketch like the fundamental theorem of optimal transport for quadratic costs. So quadratic cost is where C of xy is just the squared norm between x and y. This is the most like geometrically meaningful cost. And like this fundamental theorem all just comes from a duality principle for this Kantorovich problem, which should make sense because that's what linear programming is all about. So by the way, like when C of xy is the squared distance, then the transport cost is what we'll call the squared Wasserstein distance between mu and nu. Okay, but I'm not going to specialize to this just yet because duality is much more general. I'll just work with the general cost function C. So how does this duality work? I'm going to turn this constraint that gamma is a valid coupling into a Lagrange multiplier. So this will transform this infimum problem into like an inf soup. And then if you switch the soup and the inf, then you'll get the dual problem. And then because of like everything's convex here, actually like strong duality will hold. So the inf soup will equal the soup inf. So what does this look like? Instead of looking at gamma that satisfy these marginal constraints, I'm only going to look at non-negative gamma. And then the Lagrange multipliers, they're going to look like a pair of functions f and g. I'll show you in a second, but okay, so first we have the cost, which is C of xy. Okay, now how do we like encode the constraint that gamma should have marginals mu and nu? Well, if I look only at functions f which depend only on the x variable, then I want their averages under mu to be the same thing as the averages under gamma. So I look at f of x. And then I want this constraint.
So it will be a penalty term if it's not zero. You want it to be zero.
Yeah, I want this to be zero, because if this is zero for every function f, this is really saying like, once I marginalize out the y variable, then the marginal of gamma is equal to mu. But now I take the soup over all functions f, and then if this is violated at all, then this penalty term will give me infinity. And then similarly, I have a penalty term for the other marginal. Which looks like this. Okay, and then so now we can actually write down the dual problem. The dual problem is just obtained by switching the soup and the inf.
Once they find bounded the prime minimax, don't believe that FNG are bounded or complexly supported or something.
Yeah, sure. I'm not going to worry about the technical conditions there. Actually, like applying minimax, like, yeah, you need to be careful in infinite dimensions, but
You have to what?
What?
You said if you want to apply minimax, then
in infinite dimensions, you have to be careful and check all the conditions of the theorems, but I'm not going to do that.
yeah, Shai Moranto talked to us a little bit about this. Yeah.
So what does the dual problem look like? So I'm going to first soup over fg and then take the infimum over gamma. And in order to do this, I'm going to rewrite the problem in a better way. So first, I'll just isolate out the parts depending on f and g alone, which are f d mu plus g d nu. And then I have the other terms, which are integrals under gamma. So it looks like I have the cost function c of xy minus f of x minus g of y. Okay, so now I can just solve this minimization over all gamma. And the point is like, this thing has to be, this should be non-negative if I want to not get like minus infinity in this problem. The reason why is if this were like strictly negative at some point, then I can make gamma concentrate on that point and then send it to infinity, and then I would just get minus infinity for this whole problem. So this turns into a constraint on f and g, namely that f of x plus g of y should be less than c of xy for all points x and y. So we're going to write this as f direct product g is less than the cost function c of f d mu plus g d mu. Okay, so this is the dual formulation. Okay, and as I mentioned, like you can show under very general conditions, strong duality is going to hold. So the value of this dual problem is equal to the value of the primal problem. A special case of this is when c of xy is just it's just 1 if they're distinct and 0 otherwise. So when you think about what this looks like for the primal problem, then this is just like the probability under the coupling that x and y are distinct from each other. So that's the total variation distance. And then if you plug in this into this duality formula, you will actually get the duality for TV distance. That is the soup over all bounded functions of the difference of the integrals between u and v. That's just a remark that this gives rise to TV distance.
Everybody sees that.
Yeah, I don't want to explain in detail right now, but just mention.
Yeah, it should be easy actually.
Okay, so now I want to specialize the quadratic cost. For the quadratic cost, it's going to be convenient to think about these variables f and g in a different way. Namely, I'm going to define variables phi and psi, which are just the quadratic function minus these variables. Okay, so why is this helpful? Well, if I look at the,
Because the C of xy is this.
yeah. Well, actually, like, let me put a factor of 2 in here. That'll be helpful. But yeah, okay, so why is this helpful? Let's think about how the dual constraint translates. So the dual constraint was that the sum of these two is most this quadratic cost. But now I'm going to plug in for f and g. So I get the norm squared of x minus phi plus the norm so now I get this. And now I can subtract off the x squared over 2, y squared over 2, and I'll just get it in a product term. I'm going to rearrange this whole inequality, and you'll see it's equivalent to the following. To this constraint.
That's another now.
I mean, it's linear and phi and psi separately.
I find size, yeah, okay. But x and y here is I keep it, yeah, okay. It's I find.
Okay, now, let me ask a question, which is, suppose that one of my dual variables is phi in this new parameterization. If I fix that, what is the best possible function I can take for psi? So if you think about what this problem is, it's like, okay, I have the these variables is like this. So I want to maximize this problem, which means I want to make psi as small as possible. I need to make psi as small as possible while satisfying this constraint for all xy, right? Let's say like for all x, psi of y should satisfy this. So the best possible choice of psi is to take the supremum of this, okay? So this is the best possible choice, and the reason why this is very nice is you might recognize this as precisely the convex conjugate of phi. Okay, is everyone familiar with convex conjugates? Okay, so what this tells you is that in the dual problem, I can just restrict psi to equal phi star. That will be optimal. It starts to give you like a taste of where the connections to convexity come from. In particular, let's think about an optimal dual solution and an optimal like primal solution. Okay, I said like by strong duality, the values are going to coincide. Now, like this dual constraint that I wrote here, it came specifically from here. Okay, so if this is strictly bigger than 0, then there will be a gap between the primal and the dual. But because the optimal primal value equals the optimal dual value, this thing actually has to equal 0 at optimality. So what does it mean for us to have equality at duality? It means that actually at optimality, for gamma almost every xy pairs, I need to have that this is an equality, that phi of x plus phi star of y equals the inner product. Like this has to be completely tight for every xy in the support of the optimal plan gamma. Okay, but now there's actually a theorem of convex analysis, which says that this is true if and only if y lies in the subdifferential of phi.
What does it mean?
You can also just think of it as the gradient. Not all convex functions are differentiable, so I just wrote subdifferential, but you could just think like y is a gradient of phi.
And similarly, x is a gradient of y.
Similarly, x lies in the subdifferential of phi star. Yeah. Okay, so this is a characterization of like what the optimal xy pairs are for convex.
So if the differential of phi is the set.
Yeah, in general, it's a.
The gradient is a vector, right? So
In general, it's a set. Like what you should think of is like the absolute value function. So here, like at all of these points, this function is differentiable. Here, it's not differentiable.
no, that's not my point. Suppose it's differentiable, but suppose we look at the gradient. The gradient of phi is supposed the gradient of phi of x is a vector. No, it's
Yes.
So what do you mean that y lies there?
It lies in the subdifferential, but if it's differentiable, then the subdifferential just consists of one point, which is the
So it's
gradient.
equal. Okay, so in the differentiable case, y is the gradient of phi of x, and x is the gradient of
Yes,
phi dual of y.
that's right. Okay, so this actually like characterizes what the optimal transport plans look like. They're supported on the graphs of subdifferentials of convex functions. And in particular, if mu has a density, like if it's a continuous distribution, then actually phi is differentiable almost everywhere on the support of mu. So the reason why this is the case is like if you look at the domain of a convex function, then it's actually like locally Lipschitz on its domain. Locally Lipschitz means like by Rademacher's theorem, it's differentiable almost everywhere with respect to the big measure. If mu has a density with respect to the big measure, it's also differentiable almost everywhere with respect to mu. And so
Suppose just to get suppose we are in the plane, and I have n red points and n blue points, which describe the transportation problem, and what I pay for matching is the Euclidean distance. What does it tell me about the solution in this case?
So the discrete setting, like you might not have these differentiability properties, but you always know that the optimal transport plan is characterized by these like subdifferential conditions.
So there is no way to visualize it even in 2 dimensions, but if I just drew for you 5 red points and 5 blue points on the board, what would be the optimal weighted matching in terms of distance? It should say something about maybe that edges should not cross or something.
I mean, but that's trivial, I guess.
Well, even if it's trivial, I want
Sure.
I would love a trivial example that demonstrates this more complex. Well, I mean, do you see why matching edges should not cross? Why
if it's Euclidean,
this?
no, I don't.
Yeah, so that would be it should follow from that, right?
I suppose.
Yeah, so this has geometric content. Yeah, we are talking about Euclidean space. We are drawing a matching between points. Maybe it's a continuous distribution, but let's discretize it. We should see something about the matching that tells us these conditions are actually forbidding, trivial mistakes, ways where we could improve the matching. There will be some local improvements. Yeah, so I don't see it in this formulation, but it must be hiding there.
Yeah, you're right. So there's another way to arrive at these results, which is you can prove that any optimal transport plan, the support of it must satisfy this condition called cyclical monotonicity. And this is like a cycle condition that like I cannot take like n x points and x y points and like rearrange them to get a smaller matching cost. This should hold true for every like pairs of x y points in the support. And then there was a theorem of Rockefeller also from convex analysis, which characterize what are the sets of R2D that are cyclically monotone, and they're precisely like subdifferentials of convex functions.
Okay, that's good. So that's exactly this local improvement by, of course, like in matching theory, you also have this. You can take two matchings and take their symmetry different, you get cycles, and you see whether you can improve. So that would be the combinatorial interpretation of this subdifferential.
Yeah, like somehow convex functions are the most efficient. They don't create all these cycles. Like you could just check this by writing out the convexity inequalities, and yeah, I won't do it now, but let me like say the upshot of this is that when you transport from a continuous distribution, if mu has a density, then the optimal transport gamma is the law of x and the gradient of a convex function applied to x. Okay, so there exists a convex function phi. I guess I should write phi is convex. There exists a convex function phi such that the optimal transport plan is characterized by pushing forward x deterministically by the gradient of phi. So in particular, because this transport plan is of this form, gradient phi is the transport map, and it solves the original Monge problem in these cases. But yeah, this is also known as like Renier's theorem, and it's like the fundamental characterization of optimal transport.
Yeah, we start without any convexity constraint, and we get it out.
Yeah.
Comes up.
Yeah.
So again, this convexity is what prevents cycles of local improvement.
Yes. That's what we have here. See. Okay. Yeah, there's other questions, or I guess we could also, maybe it's a good time for a break.
Yeah, that's a good time for, but yeah, 5 or 10 minutes, but.
Sure, 5 minutes. Yeah. So the next part will be about the geometry of this optimal transport problem. Okay, so what I described up there is what's called the static optimal transport problem, because it's you have like the mass at the start, you have the mass at the end, you know like where the mass at the beginning will go, but it doesn't tell you like how the mass should be moved. And this kind of like dynamical understanding of optimal transport is what leads to like an understanding of just more generally dynamics of probability distributions. Like if you have an evolution of probability distributions, how can you understand this like in a geometric sense?
With a general cost function or with diffusion?
Going to look specifically at the quadratic cost.
But in this case, aren't the trajectory straight lines?
Yeah, they're going to be straight lines. Yeah. Yeah, exactly. Okay, so the moral of this part is going to be the question of how do we lift our understanding of dynamics from Euclidean space to the space of all probability measures. Okay, so this actually has a lot of analogies with fluid mechanics. So I'm going to present that analogy. But imagine that you have like a particle trajectory. Okay, and then in subtests, to understand the dynamics of this particle trajectory, you need to understand like this curve, its like derivative, which is the velocity, its second derivative, which is the acceleration, how they're related to each other. That's basically like classical mechanics. It's just understanding how a single particle will evolve. But now when you look at fluids, like you have a lot of different particles all moving at once, and what you're really interested in is like the collective behavior of the fluid. So this like point of view where you study individual particle trajectories, this is usually called the Lagrangian view of fluid mechanics. But then there's another view called the Eulerian view, and this Eulerian view of fluid mechanics like focuses on fields, which tell you like at every point of space, what is like say the velocity of the particles moving at that point, or like what is the mass density, what is the pressure. So let's talk about the Eulerian view. And you might think like this Eulerian perspective is going to be more relevant to optimal transport because we want to understand the evolution of the density. So the Eulerian view is like you have this velocity vector field for each time. So this is a vector field. It assigns to every point of space a vector. So that Vt x is like supposed to be the velocity of particles at x. And you also keep track of, this is the mass density. The way to relate these is like, we think of like xt, like a single particle, as being a sample from this distribution mu t, which is the mass density. Okay, so because Vt is describes like the velocity of particles at x, this tells you like how the particle trajectories look like. Namely, the derivative of a particle trajectory is just going to be the velocity vector field at that point, right? So this tells you how the particles are moving, but the question now is like, how does the full mass density evolve? Okay, and the answer to this is what's called the continuity equation. This is the basic equation of fluid mechanics, which tells you like, given the velocity vector field, how does the mass density evolve? So this equation looks like this: the time derivative of mu t plus the divergence of mu t and this vector field vt is 0. So this equation is like also encoding some kind of conservation of mass, that the total integral of mu t is going to be constant. Okay, so let's derive why this is true. And the idea is the same as how we derive the evolution of law for stochastic dynamics. We're going to again consider a test function. And then, okay, so on one hand, we can ask like, how does the expectation of this test function evolve? And here, like xt is like a random variable drawn from mu t, but the trajectories all follow this velocity vector field. So calculus will just tell you that this is the gradient of phi times the velocity of x. But that's what the vector field will tell me. It's vt of xt. And now we do the same thing as before, where we interpret the left-hand side as phi against the time derivative of the density, and we interpret the right-hand side as grad phi and this vector field with respect to mu t. But then we need to integrate by parts again, and then you get minus the divergence of mu t vt. And phi. Okay, so when you compare the two sides of this equation, then you derive the continuity equation. It's like a simpler version of the derivation we did for stochastic dynamics.
There's no noise.
Yeah, no noise.
Why is this an interpretation of preservation of mass? How do we read the divergence of mu t v t? That's supposed to.
Well, like one thing is like the integral of the divergence is equal to 0. This is as long as like you have, you know, your usual boundary conditions. So if you just integrate this equation, this tells you the time derivative of the total mass is 0.
Yeah, but that's, so, okay, the conservation of mass is a consequence of this.
Yeah.
This is a stronger one because it's a stronger set. So now comes like the philosophical part of this talk, which is like, what does this actually tell us about evolutions of probability distributions? Okay, so now let's suppose I just have some curve of probability measures mu t, and I want to understand this curve of measures mu t. For instance, like mu t could be the law of Langevin at time t. So the idea behind what we're about to do is we're going to say like, can we find a vector field Vt such that the evolution of mu t is described by this continuity equation? So if we can find this vector field Vt that reproduces the evolution of mu t, then we have this like interpretation in terms of these like particle trajectories of what the dynamics of mu t are doing. This is going to be our question. So given mu t, the curve of probability measures, and we find the corresponding vector fields that drive its evolution. And now, like, suppose that we could do this. What we're going to think of is that this is kind of going to be the tangent vector to this curve at each time t. Okay, so what is a tangent vector? Like, I mean, think about a sphere or something like that, and you picture like curves on the sphere. At every single point on this path, you have a notion of like the velocity of this curve. And this velocity of the curve belongs to like tangent space. This is like where Riemannian geometry comes in. So I really want to say, like, because this vector field Vt is completely determining the evolution of mu t, can we think of Vt as a tangent vector to this curve? Can we define like a tangent space, the space of all distributions, and then do some like Riemannian geometry? So the answer to this question turns out to be yes, you can always find a Vt that will reproduce the evolution of mu t, but we have to like be careful about how we do this because there's going to be non-uniqueness. There's actually like a lot of different choices of Vt that will give rise to the same motion. So here's There must be assumptions on this curve of distribution, right?
oh yeah, it has to be
Continuous,
yeah, it has to be basically continuous. Specifically, yeah, absolutely continuous, but just take like reasonable curves that don't jump. Otherwise, like you cannot have a derivative of the curve, right? Okay, so this is the non-uniqueness example. Let's suppose our curve of measures is just standard Gaussian for all times t. Okay, so as a curve on the space of distributions, it's just a constant curve. It's not moving anywhere. So there's an obvious choice of vector fields, which will give rise to this, and that's just the zero vector field. They're not moving. But there's actually another vector field that you can write down, and it's just the rotation vector field, right?
just because it's a symmetry.
Yes, because the Gaussian is rotationally symmetric, right? So if my particles were like constantly swirling around in circles, then at every time t, I would still like preserve the right distribution mu t. So now like if I just start with the curve mu t, which is Gaussian at all times, and then I ask like, okay, which explanation for the dynamics of mu t makes more sense to you? Then, well, we heard about like Occam's razor, right? We should take the simplest explanation. Somehow like this one is not very good because there's a lot of wasted movement of all the particles. All this like swirling is not really contributing to any change in mu t. And this idea of like trying to find vector fields which don't have wasted movement, this is going to be like very related to the idea of optimal transport, right? We don't want to transport by taking unnecessary movement. So the physical principle that underlies this is that given a vector field Vt, what is this quantity? So this is like the squared norm of the velocity times the mass density, and then I integrate over all of space. So mass times velocity squared, that's called the kinetic energy, right? So like a physically motivated way to find vector fields that have like no wasted movement is to find the Vt, which minimizes the kinetic energy, subject to reproducing the right behavior of Vt. So we're going to set, let's say like maybe Vt star. I'm going to take the best vector field V, and it has a constraint, which is that the divergence of μtv should be minus the time derivative of μt. Remember, like μt is given to us, so the time derivative of μt is known, μt is known, so this is just a constraint on the vector field V to make sure it reproduces the same movement, but we're going to minimize this kinetic energy. And this guy is just the L2 norm of the at the current distribution. So that's the way we're going to call it. Okay, and it turns out that there's a the solution to this problem is that Vt star is the gradient of some function psi t. Okay, this is a characterization of the minimizer. This psi t is of course related to optimal transport. Psi t here is not convex, but the way you should think about it is like, suppose I start from μt and then I go a little time later to μt plus h. The way to do this with the least amount of wasted movement is to take the optimal transport between these distributions, which is a gradient of a convex function. If I have the gradient of a convex function, what is the velocity vector field associated with this? It's like where I go minus where I started, which is just the identity mapping, divided by the time. Okay, so what you can show is that this thing is going to converge to the optimal Vt star, and because this is a gradient of a function, then this is like preserved in the limit. But let me give you like another reason why that's true.
It's actually very close to a convex function. I mean, it's just shifted by.
Yeah, but yeah, this can be like an arbitrary function. So
With the arbiter in general, it can
Yeah.
be anything.
Yeah.
Because it seems like you just subtract identity from the gradient.
yeah, but
Like you can add some function to phi t some.
but this h is going to 0,
Yeah.
so you're really subtracting off larger and
I know,
larger.
yeah.
Yeah.
I'm trying to figure out what maybe it's.
And
So
like,
you're saying it can be an arbitrary.
yeah, because it's now the displacement vector. It's like subtracting off what you started from. So let me just give a proof of this though, which is like let's look at this constraint that the divergence of μtv is equal to minus partial t vt. So the constraint is that okay, but based on the same derivation that we did for the continuity equation over there, this is completely equivalent to Vt satisfying this this test function. So for all test functions, let's say f, I want that the time derivative of f under μt is equal to grad f dt. Okay, so I'm claiming like this was a derivation that we already did, that this constraint is equivalent for all test functions f having this. Now the point is like, look at the left-hand side. Here, there's always a gradient of a function. So like Vt only acts upon gradients of functions. So what that means is like, I could take the orthogonal projection of Vt onto the space of gradients of functions with respect to this inner product. Now, if Vt had any component that was like orthogonal to the space of gradients, then it would not change this left-hand side at all. So the constraint wouldn't care. But since we're minimizing the kinetic energy, we want to eliminate that orthogonal component. So when you do that, you should end up with Vt also being the gradient of a function. So Vt only acts on gradients. Okay, so with that as motivation, we can now define the tangent space. The tangent space at a measure mu to the space of distributions is going to be like all gradients of functions. Okay, so for technical reasons, like the way that you might actually make this precise is that I start off with a nice class of functions, like smooth, compactly supported. And then I take the closure of this space with respect to. So this is the formal definition, but you can basically think like, okay, this, it's a gradient because these are the only optimal vector fields that we care about. And the way that this is a tangent vector to mu is that if you like infinitesimally push forward by this gradient of a convex function, then it will induce some movement of the measure mu.
It's a linear space by definition.
Yes. And of course, like we're going to equip this with the L2 mu norm. Okay, so these are the two ingredients of a Riemannian manifold: is a notion of a tangent space and also a norm, which tells you like how to analyze movements. Now, like let me like identify geodesics in this space. As Avi said, we're just going to be straight lines. Let's see.
So T mu is the tangent space at mu. For every distribution, you have a tangent.
Yeah, and the picture is like we have some like plane of like infinitesimal directions that you can move it. So let's see how the geodesics work and also the distance. So generally speaking, like in Riemannian geometry, you start off with what's called the Riemannian metric, which is like a norm, like an inner product on every single tangent space. Given this Riemannian metric, you can define the distance between 2 points. The distance between 2 points is defined as follows. You look at all curves. Let's say that this is points P0, P1. You look at all curves which start and end at P0 and P1, and then I minimize the length of the curve. So what is the length of the curve? So the
M is your manifold.
Yeah.
M is the space you're in.
Yeah. Okay, so you can define the derivative of the curve because it's an element of the tangent space, and then you measure the size of this velocity, in other words, the speed of your curve by the inner product at that point. So when you integrate this is the total length of your curve. So what this formula says is I could define a notion of distance between 2 points by finding the length of the shortest curve, joining them, and this is called the geodesic joining these 2 points. This minimization problem is not so great. The reason why it's not so great is because given any curve P, another minimizer is just formed by reparametrizing this curve. I just traverse the same curve, but like faster at some parts and slower at some other parts, something like that. I'll still get another minimizer for this. So actually a more convenient variational problem is a variational problem for the square of the distance. It looks the same way, but we're gonna put this way. So now this is called the energy of the curve. And the advantage of this is that any minimizer to this second problem also has the constraint that it's traversed at constant speed. Okay, so this integrand is going to be independent of time at optimality. Okay, so that was some background on Riemannian geometry. So now what I want to know is what is the distance associated with the geometric structure I defined over the space of distributions. And it's going to turn out to coincide with the Wasserstein distance. So that's what I want to show now. Is that okay? So the Wasserstein like the geometric structure that I defined is really like related to optimal transport because it's like the Riemann geometry underlying the squared Wasserstein distance. Okay, so how do we do this? So let's say I have 2 measures, mu 0, mu 1, and then I'm going to look at the I want to find the minimizer over all like curves and their tangent vectors of this guy. So here, like the infimum is taken over like the mu's and the v's, where the mu's have to join mu 0 to mu 1, and the vt's have to be the tangent vectors of vt. But remember, like vt is the velocity vector field. So if we switch back to the Lagrangian interpretation of things, this is the same thing as the expectation of xt dot, where xt is like a random variable, which like a trajectory that's sampled from this like mu t vt pair. And now I'm going to apply Jensen's inequality to say this is always lower bounded by the expectation of I just pull the integral inside the square norm. And then if I integrate the velocity, this is just the same thing as the difference between the endpoints. Now, like this constraint on my distributions means that x0 has to be distributed according to mu0, and x1 has to be distributed according to mu1. So x0, x1 is actually a coupling of the two distributions, mu0, mu1. So because the Wasserstein distance is the smallest coupling cost, then I know that this is only bigger than the squared Wasserstein distance. And now I'm going to argue, like, when can we make these two inequalities actually equality? Okay, so this inequality is going to be equality if x0, x1 are optimally coupled, right? So let me just write that as saying x1 is, this optimal transport map applied to x0. So they're optimally coupled, in which case that would be equality. Now, this inequality, this is the equality case for Jensen's inequality, but the equality case is exactly when xt dot is constant. So what does that tell you? This tells you that the curve joining x0 to x1 is traversed at constant velocity. So it tells you actually xt is a linear interpolation between x0 and x1. It looks like this. Okay, so now we have a dynamical understanding of what the optimal transport problem is doing. Like what we do is we first compute the optimal coupling between the endpoints, and then we just join the start to the end via straight lines. And that is the optimal transport geodesic. But specifically, like if I say mu t is the law of xt, where xt is defined in this way, then mu t is called the W2 geodesic. So now we've identified what are like the shortest paths in this space, and it has like a very satisfying answer. Yeah, I think we're basically ready to talk about how to define gradient flows on this space. So I'll just like tell you how to define gradient flows. I will identify the Langevin diffusion as this gradient flow, and then that'll be it for today. I was planning to do more, but yeah, got time. Maybe I forgot to mention, like, because these are all equalities, this tells me the distance function induced by that Riemannian geometric structure is the squared Wasserstein distance, as I claimed. Okay, so gradient flows. So how do we define like the gradient of a function in Riemannian geometry? In this case, it's going to be a functional over the space of distributions. The gradient is defined in a pretty natural way. It says that for any curve mu t, if I differentiate this functional along the curve mu t, then the gradient is the unique element of the tangent space. This has to belong to the tangent space. Such that this equality is true, and Vt is the tangent vector to the curve.
So you are given all these you have the vector. Vt is given.
Yeah. So for any curve mu t, I know that associated with it as the tangent vector is Vt. Right, that was what I argued over there.
Yeah.
And now I'm saying like for any of these curves mu t, when I differentiate this functional f along this curve, I should just get an inner product between the tangent vector to the curve and a certain element of the tangent space, which is defined to be the gradient of f in this geometry. Okay, so this is how we define the Wasserstein gradient of a function. Okay, so we're going to compute this Wasserstein gradient for the KL divergence. So this is the function we're looking at, the KL divergence from mu to pi. And let's recall that pi is of the form e to the minus v, because we're going to use this. Because this is the integral of mu log mu over pi. But if I take log of 1 over pi, that will give me v, my potential. So I can write this, split this into two terms. I have the integral of the potential with respect to v, with respect to mu, and also the entropy of mu. Well, this is the negative of the Shannon entropy. And then there's an extra constant because I only talked about this up to proportionality, but of course we don't care about the constant. Okay, so this is called the potential energy functional. This is called the entropy functional. We're just going to, okay, let's call this like curly v. Let's call this curly h. And we're going to compute the gradients of these separately, just according to this recipe. So let's let's do this starting from v. Okay, so I start off with mu t, vt, like a curve mu t and the tangent vector is vt. And then I want to compute what is the time derivative of v, integral v along ut. Okay, but if you recall, this is exactly like how we even started at this whole continuity equation derivation, is that the integral of any test function against ut is the gradient of v and the velocity vector field ut. Okay, this was just from the derivation of the continuity equation. So what does this tell you? This is like the mu t inner product over here. So this looks like our candidate for the the Wasserstein gradient of this potential energy functional. And you can check this is indeed belonging to the tangent space because it's of the form gradient of some function. So I know that this is a tangent space. So actually, the Wasserstein gradient of this potential energy function is the gradient of V. So you'll notice like actually this doesn't depend on mu at all. So this is like a constant, it's like a constant gradient, which kind of makes sense because this is a linear functional of mu. And also this is a vector field, right? The gradient is a vector field. And based on the way I've set it up, all the tangent vectors are like vector fields. And then we just have to do the entropy. Okay, so now we're going to differentiate the entropy along this curve, the integral of mu t log mu t. Okay, so what is the derivative of mu log mu? It's log of mu plus 1. So by calculus, this is log mu plus 1 times the time derivative of mu dt. Okay, but remember, like the way that mu and v are linked together is via the continuity equation. That's what it means for vt to be like the tangent vector to vt. So because of that, I know this equals divergence of mu t vt. And now we can integrate by parts to pull like the divergence off of these terms. And when I do that, I will get grad log mu t dvt. Okay, like the divergence turns into a gradient hitting this, and then the one gets killed. So I get this. And now the same story, like this is the right-hand side of the definition of my gradient. So this is my candidate for the Wasserstein gradient. And it's also the gradient of some function. So therefore I know it belongs to the tangent space. So I've identified the Wasserstein gradient of the entropy at mu is the grad log density.
You already raised the one for the V term.
It's up
It's
here.
up there, yeah, sorry.
Okay, so I computed the gradients of the potential energy and the entropy. So now I know what the Wasserstein gradient is of the KL. Now the question is, what is a gradient flow? A gradient flow is a curve mu t such that the tangent vector at every time is just the negative of the gradient. So it's always following the direction of steepest descent. So the gradient flow, I want the tangent vector to my curve at time t to be just minus the gradient. And so based on what I calculated, it's minus grad v minus grad log mu t. And what does it mean for like this to be the velocity vector field to my curve mu t? It means that the evolution of mu t is governed by this continuity equation. So partial t mu t plus divergence of mu t vt is 0. So if I plug this in for what vt is, this tells me what the gradient flow looks like. It's divergence of mu t times gradient v plus gradient log mu t. Okay, so this is the gradient flow for the KL divergence in this geometry. And now we just want to compare this back with the Fokker-Planck equation over here. If you compare these, you can see the only difference between these two is that here I have the Laplacian and here I have some other term. But those two terms are equal by calculus because if I look at the divergence of mu t grad log mu t, so the gradient of log is going to give me gradient of mu t divided by mu t. So then these cancel. So I'm left with just the divergence of the gradient, which I said was the Laplacian. Okay, so this identifies the evolution of law of the Langevin diffusion with the gradient flow of the KL. And now we also have another interpretation for the two terms in that equation. You can really see that like this term.
Wait, can you repeat this conclusion that we see that the gradient flow, so what you observe for the Langevin equation is the gradient flow on this Wasserstein space with respect to the KL divergence metric between the two.
No. So the KL divergence is the objective function, and the metric is the
Sorry,
is
yeah,
the
that's what
Wasserstein
you
distance.
minimize. The metric is Wasserstein, you're minimizing the KL.
Yeah. By the way, like so in one of the original papers, Otto, the way he described it is that like the geometry of your space is encoded in the metric, the Wasserstein distance, whereas like the objective function encodes the thermodynamics, the relative entropy. So this is like a interesting physical consequence. Oh yeah, so these two terms that we derived for the Fokker-Planck equation, you can see this part is coming from the gradient flow of the potential energy. Like we're just following the direction of minus grad V in order to lower the potential energy. This term we derive from Brownian motion, and the Brownian motion is the gradient flow of the entropy. When I try to like increase the entropy as fast as possible in this Wasserstein metric, then I end up with the Brownian motion or the heat equation.
So where specifically, how do you get the Brownian motion? Where do you see that that continuity is actually just Gaussian, just a Bellman?
I mean, when we derived this equation, this term really came from the second order term in the Taylor expansion, the Ito correction. If you had no potential, then this would just be the heat equation, which is describing the evolution of Brownian motion. So this term, this Laplacian Lut, we saw like in the Wasserstein context, it could be interpreted as this term. And this term was really just the gradient of the entropy term. Okay, so I mean, this tells you like an interpretation of the Langevin diffusion. I didn't really get to tell you like why this perspective is like useful, I suppose. But the point is like this geometric structure, first of all, like it gives you like a link between optimization and sampling, because now like the Langevin diffusion, it was like this stochastic process seems at first like to have nothing to do with optimization. He is actually following a gradient flow of some objective function. So now we can try to understand the connections there. And then also like there's all this like general theory for when do gradient flows converge. So gradient flows converge in particular if your objective function is convex or strongly convex, but there's like other conditions for gradient flows to converge. So you can actually then try to check those conditions for the Langevin diffusion. So I'll just mention this. Without going into the details, but okay, so suppose that your potential function is strongly convex, then this is equivalent to the potential energy being strongly convex on Wasserstein space. And also, it's known that the entropy function is convex on the Wasserstein space. So when you put this together, this actually gives you a condition for the strong convexity of the KL divergence over the Wasserstein space. And so these will actually lead to fast convergence of the gradient flow, which is the same thing as Langevin. Just another remark, like this convexity of the entropy, like we know that mu log mu is just convex along the usual interpolation between two measures. Like I just interpolate their densities. This is saying something different because this is convexity along Wasserstein geodesics. It means if I take two measures and I connect them via the Wasserstein geodesic, which does not just like interpolate the density, it pushes forward the densities. Then it's convex along those paths. And this is actually non-trivial. One way to see that it's non-trivial is that this fact is equivalent to the non-negative curvature of Euclidean space. In the sense that you could like set up everything I talked about on a Riemannian manifold, like diffusions on a Riemannian manifold, KL over the manifold. And what you'll find is actually like in that setting, this term is really related to the Ricci curvature of your manifold. Like if your Ricci curvature of your manifold is positive, then the entropy becomes strongly convex on that manifold. So yeah, this actually tells you that this optimal transport perspective captures like the geometric information about your space. And that's like led to the whole like theory of synthetic Ricci curvature. This is also like a big development in geometric analysis, but essentially like it allows you to define like what are limits of Riemannian manifolds and so on, all through this optimal transport perspective. That was just kind of broader context into the math literature. Basically, content.
You're stopping.
Yeah.
Okay, great. Question?
Okay. Well, what exactly does fast converge mean in your last theorem?
Yeah, so under these two conditions, you can get these two results, for instance. The Wasserstein distance through the stationary distribution is going to converge exponentially fast. This is reflecting the general property of gradient flows that if you take the gradient flow of a strongly convex function, it's contractive. And you can also get a convergence in terms of the objective function, which is a KL divergence. So the KL divergence also decays exponentially fast. And these results you can also obtain via other means. This isn't like the only route to get there, but this is really more about the intuition or interpretation. Plus, like there are actually some samples.
This is general for gradient flows.
Yeah. So under strong convexity, you replace this with the square distance, and you replace this with the objective gap.
What happens if you were looking at L1 instead of KL divergence? Your optimization.
Like TV distance?
Yeah, the statistical distance between the two distributions.
Well, the gradient flow of that in this geometry would not be the Langevin diffusion. It would be some other process. And because everything here is over the space of measures, then like the resulting dynamics that you get out, it wouldn't be clear how to implement it. So kind of one of the magic things that happens here is that the Wasserstein gradient flow of this KL, which gives you some PD for mu t, this seems like very hard to implement, is actually like implementable via this diffusion process. And therefore you can discretize and just run a random walk on your computer.
So when he Langevin proposed this diffusion process, did he know about the Wasserstein distance? No.
No, Langevin, I'm not sure exactly when that was, maybe early 20th century or something like that. This is around the time of like Kolmogorov and trying to understand like, like gas particles that are like colliding with each other. So the collisions are modeled by Brownian motion. Einstein also was like looking at this. So yeah, it dates back to that. But then like this perspective of Langevin as a Wasserstein gradient flow, it's due to this work by Jordan, Kinderlehrer, and Otto in 1998. And because of this, like this is very commonly referred to as JKF. This is like one of the top 10 most downloaded papers on SciEm.
More questions? All right, thanks.